So, good morning, everyone, and thanks all for joining in. So, today we will start with KNN or K nearest neighbors and how it is used for classification. So, this algorithm is mainly used for classification and regression, both of them, and but mainly we use it for classification. Also, when I was going through some of the articles, I found that in most of the machine learning cases, the main problem that we are asked to find is for classification, where we have to make some decision that if it is a yes or no, or may not be binary, it could be a multi-level decision. So mainly when we come across classification problems, KNN is a very good technique to actually work with, and it is quite easy to understand. So it is very lame and even easier to understand compared to logistic regression, and has and its working can also be well explained. So someone who is very new to this machine learning techniques, for him also KNN is a uh, even if he is new to this techniques, machine learning will be a very I would say easier to grasp or is easier to understand because there is not much mathematical terms associated with KNN. So let us start with today's session. So mainly, as I said earlier, mainly we have a classification problem. For that only KNN is used. A regression problem for regression model, it can be used as well. Only difference is that in classification we take the vote of the nearest neighbor, and in regression we take the average of the nearest neighbor. So that is the only difference. Apart from that, both of them have the same algorithm. So why is it so that KNN is such a good technique? First of all, it is very easy to interpret. So if I start rating all this algorithm on on a scale of 1 to 3, and if I want to know which one is better on these three parameters, like is to interpret the output, calculation time, and predictive power. So taking these parameters, KNN is quite good. It stands good in all three parameters. So that is the reason why KNN becomes such a good or widely used or such a handy algorithm to be used. So what is actually this algorithm all about? So let us understand. For example, let's say in very layman terms, let me draw and explain. So let me say that I have only two variables in my data set, and on basis of that I have to make a classification on the third variable. So these two variable will determine how will be my third variable classified. So let's say if I and I have both of them as a continuous variable. For the time being, let us consider only for the continuous variable, not for the categorical variable, and we will see how will deal with categorical variable as well. So let's say I have something like this two accesses for two continuous variable, and here I have plotted my two classifiers. Like this is one, this is an x, this is a plus. So plus here denotes that it is of another kind, and cross denote it is of other kind. So what will happen is my k nearest neighbor. So suppose I have a on this scale a new out of bag sample comes in, and the point for that sample is somewhere here. This is a 0, or 0 denotes for a new sample. So what it will do is, on the basis of this graph, it will try to determine who are my neighbors, who are more closely related to me. So this looks more like a let me- yeah. Now it looks more like a plus sign rather than a cross. So this is a plus sign, and this will be a cross. So these three are of one kind and this is of another kind. So on the basis of k nearest neighbor, it will try to determine in what way I have to classify this new sample. So let's say if I have value of k equal to 1, then I think this plus sign is the most nearest, I would say, sample to this. So it will take its value as plus. So for k equal to 1, it will become plus. Now, if I have k equal to 3, let's say, then there are three nearest neighbors. And out of this is of one type, and these two are of another type. So what happens is it becomes a cross. So if my k value was 1, it was plus, and if my k value is 3, it has become a cross. Now let's say these are the four samples that I have altogether currently, and if I make it as 4, value of k as 4, then this classification becomes again x. So this is how k nearest neighbor algorithm works. So when an out of bank sample comes in, it try to determine that in which classification I should put this new sample on the basis of its nearest neighbor. If I'm considering only one nearest neighbor, then on basis of it. And as I keep on increasing my k value, I keep on getting the results. So there are some issues and there are some problems in determining the value of k. That what value of k should be appropriate. Like you have seen here, if I keep on changing my value of k, my results also keep changing. So there are some challenges and there are some techniques as well through which we can determine the value of k. Okay, okay, Arun. So which part did you miss? Okay, so here as I mentioned, so for k equal to 1, I think you have understood that it goes with plus. So it is classified as plus, right? Now let's say if I have k equal to 3, so these three are the most nearest uh, samples that I have. Okay, I will try. So I have some charts as well, so I will try with a different explanation as well. So these are the nearest three neighbors that I have at the moment. So on basis of these three, so here I have two crosses and one plus. So two votes for cross, one vote for plus. So in that case, my cross wins and I have cross. Now here, out of these four samples that I have, three votes for cross, one vote for uh, this plus. So majority vote goes with X. So I have classified my new sample as X. So this is how it works. So does it make sense or is it still unclear? Okay. Okay. So I will explain it more detail. So I think the chart that I have drawn is not so good. So I'll try to explain in a better way. So let us understand with these simple terms. So k-nearest neighbor classify new object according to the outcome of the closest object or the outcome of the several closest objects in the feature. Like I said in the graph, the closest object that we have on the basis of which it tries to test. And as I said, it is the most simple and the most layman term, most naive kind of algorithm that we have, and it is easy to explain. And an object is classified by the majority vote of its neighbor. So with the most of the neighbors have a majority vote. With that, the new sample goes, and the new object is being classified to the class that is the most common among its k neighbors. So it is So in calculating the distance, there we have many kind of techniques for distance calculation. So distance, as you know, and there could be many kinds of distances as well. One could be Euclidean distance, which we all must have done in coordinate geometry. So this is the basic formula that you can see. So this formula you all must be familiar with, that you have done in your coordinate geometry, where there were two vectors and you have to find the distance between the two. So this is mainly the Euclidean distance. Another is a Manhattan distance. So there is a only one difference in Manhattan is that this square gets removed, and instead of this square distance we are only taking the mod, and this power gets removed. There is no power of 2, it is actually power of 1. So mod of distance, and then it is calculated. So it is mainly the absolute difference between the two, that is Manhattan distance. So in most of the cases we use Euclidean distance only. So, and this is mainly when we have our variable in continuous, in a continuous variable. uh, and also there is one challenge with this. So anyone can understand what is the challenge in this Euclidean distance. If I'm calculating it like this, so what is my problem here? So anyone, you can unmute yourself and speak. Mm, no, no, not only one observation. It works for everyone. So that is not a issue. No, no, the issue is already mentioned in the slide itself. So let me explain you in this R script. So suppose, let's say I have a variable like income, and I have another variable as age. Now let's say my income is supposed to vary from let's say 10k to 200k. So this is my variation of income. And let's say my age, and how my age is supposed to vary. Age is only supposed to vary from 10 to let's say 100, at max 100. So you see, if I try to calculate the distance between them, I will always income will have a larger impact on the Euclidean distance. So here if you see, if I calculate on that basis, then income will always have a upper edge on uh, upper edge over my age. So that is the reason, that is a problem that we come across in this Euclidean distance. So how to mitigate this problem or this error? That we make a scaling or we make a normalization. So that is the way we deal with it. So both income and age are brought to the same scale, and then we start working with it. Okay. So that is what I have mentioned here. Uh, if there are only one feature, Euclidean distance is the absolute value of the difference. It is usually recommended to standardize the feature variable in it if their units are quite different. Otherwise, more weight would be given to feature variable with larger units. So mainly we make a normalization where I always prefer to make the mean 0 and standard deviation 1. So on basis of that, we make a scaling, and then we do this Euclidean distance measurement. So hope it makes sense now. Okay. And there we have a Hamming distance. So uh, for anyone who is from electronics and communication background, I expect there would be some people from electronics and communication. And if you have studied communication, then you must have come across Hamming code or Hamming distance, right? So, yeah, Shashi, do you remember Hamming distance or Hamming code? Okay, okay, no issues. So mainly here what happens is when I have my variables in category. So mainly in categorical variable, what I do is I try to calculate the distance on the basis of number of matches that I have got and number of non-matches that I have got. So in binary, what I do is I make it 0 and 1. And what happens here is if my both are 0 or both are 1, or let's say my x and y both are same, then distance is 0. If not, then distance is 1. So this is mainly the Hamming distance. And on basis of this, I try to calculate that how many matches that I have got and how many non-matches I have got. And based on this, my distance is calculated. So this is mainly the concept of Hamming distance. And there we had in communication we had something like Hamming code, so that is a bit different. The same concept, but there was some application there, so we will not get into that. So this is mainly the working of Hamming distance, where we work with categorical variables. So this is one example of k nearest neighbor. So like I did for previous one. So let's say here this is my new sample and I want to classify it either in class 1 or class 2, and my value of k is 1. So based on the one nearest neighbor that I have, it will try to classify. So the most closest neighbor that I have is a square box, a blue color square box. So if my k value is 1, I will classify it in class 1. Now let's say if I have increased the number or the value of k, I've increased it to the value 3. Now the circle has gone with become bigger and with larger radius, and it has accommodated 3 samples here. And on basis of the voting between these classes, it has come across that triangle has been voted twice and has got 2 votes, and square has got only 1 vote. So it will go with triangle. So now it will classify this sample into class 2. So this is how k nearest neighbor works. So you all can see that deciding value of k is a challenge here. So I keep on making some changes and I come across with some other value of my sample, my new autoback sample. So there is a challenge here, and there are some mitigating factors that we have to check, that how we can minimize the error. A similar example here as well. So I have my sample, a triangle, blue triangle somewhere here, my orange circles here, and my green squares here, and a new sample comes in. And this I have to predict in which cluster or the which classification it will go. So, so yeah, there is a difference between the two. I'll also explain what is the difference between KNN and clustering. So here I will try to make on the nearest so on the certain value of k, I will try to determine which is more closest, and on basis of which I will try to explain or try to determine which class it will go to. So, one question to all of you: uh, is KNN supervised learning or us unsupervised?
Supervised machine learning.
Okay, but why?
Actually, in supervised learning, there are we use the regression techniques, classification techniques,
Mm-hmm.
and unsupervised learning, in which uh, we consider only there is no categorical variable like or no regression techniques we use.
No, no. Uh, okay. Anyone else want to try? Dinesh, it is good, but anyone else want to try? Correct. Absolutely correct. So, see, there is a difference between supervised learning and unsupervised learning, and you need to understand that what is the difference between the two. In supervised learning, we have our responses known, or the one that we want to predict has been already labeled. So, for example, let me explain. In linear regression, our y variable was known for some of the training dataset, and then in the test dataset we wanted to predict. So we already had a knowledge about how it will be. In logistic regression also the labeling was already done. So knew that for a part of dataset that it is that for some of the cases it has been classified as 1, for some of the cases it has been classified as 0. But in clustering, what happens is you don't have any knowledge or any prior information that what should be the minimum number of clusters that you should decide, or I would say uh, what should be the strength of the cluster, how many samples should go in a particular clusters. So these things are not there. KNN is a supervised learning, and there is a reason for it, because I already know that my previous samples are put into this classification. So let's say this is omega 2. So all these samples belong to omega 2. All these samples belong to omega 1, and all these samples belong to omega 3. So already labeling is done. It is when the new label or a new sample comes in, for that I have to predict whether it will go into first category, second category, or third category. Otherwise, my training dataset already has the label, already has the categories in which it has been classified. So what happens is when on the basis of test dataset I want to make a prediction, it is a supervised learning. When I already have my response variable known, then it is a supervised learning. And clustering, there is a difference. Clustering, I don't have any knowledge, any prior knowledge that how it should have been segregated or segmented. So a good example would be, let's say, mm, uh, for suppose I have a bowl and there lots of fruits are there. So I have apple, uh, mm, uh, I would say banana or oranges. So in that previously I don't know that, or let's say it all has been labeled that this is apple, this is banana, and for suppose a new sample comes in, a new fruit comes in which I don't know, but I have to see the characteristics. If this new fruit is more closer to which of the fruits that I have, or which or the fruits that has been classified. So I will take the amount of nutrients that are there in banana or apple, and on basis of that, I will try to make a prediction that new fruit should be in which category, which label should I provide? Should I provide it as an apple or a banana or an orange? So that is the case. In clustering, what happens is, suppose I have fruits and vegetable mixed up. All of them are have been mixed, and I don't know what are my fruits and what are my vegetables. So there, having no prior knowledge, I have to segment out all my fruits in one category, all my vegetables in other category. So having no prior knowledge, and now I have to start labeling them, and then the clustering works. When I already have the label, and on basis of that label I have to predict something new, then KNN works. So hope it is clear now. So let me proceed. So there are some drawbacks for the majority voting. What happens is, as I said earlier, when I increase the number of the value of k, so the smooth or the categorization, the segregation between the classes becomes very smooth. So that is a major drawback. What happens is, let's say 70% of the my samples are uh, 1 and 30% are 0. So if value of my k is very high, so it will take the majority vote, or say the 30% or the 70% one will dominate my result. So that is why you need to optimize your value of k, so that your noise is also reduced, and also there is no majority bias in your classification. So that is why an optimum value of k should be chosen. So here if I go with this slide, a drawback of basic majority classification of k-nearest neighbor algorithm is that classes with more frequent outcomes tends to dominate the classification of new object. Because of their larger number, they tend to show up more often among the k-nearest neighbor among the neighbors when the neighbors are computed. So like I said, if one of the classification or one of the labels are more, then and if I have increased my value of k, then it will tend to go towards the majority. The k-nearest neighbor algorithm is sensitive to the local structure of the data, and its accuracy is affected by the presence of noise or irrelevant features. The best choice of k depends upon the data. Large value of k tends to reduce the effect of noise on the classification, but will make the boundaries less distinct, or it will be more of smoother. It will try to smoothen up. A good value of k can be selected by cross-validation. We will see what is cross-validation and how we can select the optimum value of k here. In binary two classes classification problem, it is helpful to choose k to be an odd, as this avoids tied votes. So last line, if I say what is the meaning of this last line and why it has recommended me to take the value of k as odd, why not even? Okay, so let me explain that how it works and why we should only take a odd, not an even. So let me explain it in this. So let's say if I have two classifications, one is my A, another is my B, and these two are labeled as A and B. And now I make k equal to 2. So what will happen is, on the basis of nearest 2, it will decide. So let's say I have A over here, I have B over here, and I have my new sample somewhere here. Now, if I have a value of k equal to 2, So these two are my most nearest one. Okay, and I have a equal distance, or let's say distance is not a parameter here. I have to select nearest two. So both of them are there. So in case of voting, what will happen is A will get one vote and B will get one vote. So there is a clash between the two. Now this sample will not understand that where it should go. It should go either with A or it should go with B. So this is the problem with if value of k is an even number, not an odd number. There could be chances that there will be a clash between the two votes. The two votes will be same, and that is why it is recommended to have a odd value of k. So in case now what happens is if here I have another a and this a is also one, so so this a actually become two. The vote becomes two now. So it has two votes, B has one vote. So it will now go with A. So hope it makes sense that why we should take a value of k equal to 3 only when there are two classifiers. So two classification. In case of more than that, even is also a good value to take. But otherwise, if I have to make a binary classification, then odd is recommended. So hope it makes sense.
Okay.
So here is a good example that what happens if I increase the value of k, if I keep increasing it. So here I have, if you see the boundaries are very distinct or very minutely traced boundaries when the value of k is 1. So only on the basis of the nearest neighbor it has made the classification. Or you see even these two samples are quite close to each other and hence they have made their own uh, territories here. As you can say, background is red. So this is what happens when k value is quite low. As I keep on increasing the value of k, you will notice that this boundary becomes very smooth. So you see, this is the kind of boundary that we have. If I keep on increasing the value of k, now see, the boundary has become very smooth. Although there is some misclassification and it has gone to some other uh, labels altogether, but as you can see, the kind of boundary that I'm getting is very smooth. So that is the problem with increasing the value of k. It becomes very smooth, and when you keep it very low, then it is prone to noise. So increasing the value of k will reduce the noise, but also it will smoothen out the boundaries. So that is why it is always recommended to choose an optimum value of k, where my noises are also minimized and also the boundaries are well distinct, not so smooth. So here is a normal error plot that we have, that as the number of k increases, my error also goes high and my misclassification also uh, tends to increase. So here one more example. What happens is if my k value goes high as infinity or very high value, equal to my number of samples that I have. So what will happen is my majority vote will start to dominate the uh, classification. So if my reds are 70%, so in any case if a new sample comes in, so it will always be classified as red. So because this is always in majority and k value is very high, so always red is going to win in that case. And k value is too low, then even what happens is uh, only the closest value is chosen, not a general estimate of other. So let's say what can happen is uh, If I have that picture, I will try to explain you. So this is somewhat like that. So if my k value is quite low, it has chosen some like this. Now let's say if this box was not here and it was a bit farther, or let's say it was, or I would say, mm, so here what happens is, you can see I have kind of made a kind of partition here. So it goes somewhere like this. So my new sample could have gone in the either way. It could have been classified as a triangle, or it could have been either classified as a box. But here what happens is my value of k becomes quite crucial. That which value should I? On a visual inspection, it might at first look like this should belong to this red triangle because it is quite closer to it. Though we have a closer value of box as well, but most I could say that box values are also quite far apart, and this might be an outlier, or this might be this is a box value, but not quite of a normal trend that a box should be here. A boxes are mainly placed in the outer circle, outer part, and it is more closer to a triangle. In that case, if I'm taking value of k as 1, what happens is this box is actually a noise. It shouldn't have been here, but it is here. So it becomes a noise in that case, and my classification goes with noise. So value of k, if it is less, then my noise starts dominating the classification. And if my value of k is very high, then majority starts dominating. So that is the reason that always look for an optimum value of k. So now the most interesting part, let us start with the data set and try to understand. So a lot of theory that we have covered till now, let us understand it practically. So here I have a data set of forensic classes, that how my classes should be classified. So this data set is there in the package mass uh, library. Load that, and there I have FGL, that is forensic classes. So let us explore the dataset and try to understand what is there. So here I have these elements. This is, I think, our index or refractive index, and these are the uh, I would say the elements that are present in my glass type. So this is my glass type, and these are the elements. So I have here sodium, magnesium, aluminum, silicon, potassium, calcium, barium, and iron. And these are in some proportion or in some numbers that I have. And these are types of the classes that I have. So let us look at how many types of glasses that are there. So I to
Okay.
understand what was. So this is a factor. So levels of FGL and type. So I have here 6 types of glasses with me, and this is one I want to predict that how it should be labeled. So here I have a number of observation of 214, and let us try to partition it and try to understand that how it will score in my test data set. So first have a look at the data set, a visual look or a visual plot, and try to understand that how it should be there. So what I'm doing is I'm making a plot with all the elements with uh, the type of the mm, glass that it should be. So on basis of refractive index, if I say, so this is the kind of box plot I'm getting. So almost same, only for the part of con, it is more varied. Otherwise, more or less, they are having the same range refractive index. Uh, Aluminum content is quite high in some low, quite in some of the glasses, and quite average in some of the others. Sodium also, I can see the trend here. Magnesium for first rate is quite high, and for other,
Ankit,
yeah.
Ankit, can you zoom this picture, this window
Okay, okay,
picture?
sure,
Yeah, plot window. Can you zoom?
sure. So now it is good. Okay. So
Yeah.
here, as I was saying, for refractive index, if I say, and all the glasses that I have, so more or less the same variation. Here, for head, aluminum content is quite higher, and also for con, aluminum content is quite high. Others, I also say it's more of a same trend, but sodium is quite higher in table and head. Magnesium, I have higher content in these types of classes, but otherwise magnesium content is low here. Table has a quite high variation, though average value is near to 2, but it also can be 0 or higher as well. Head is more or less nothing, but I have few outlier values here as well. Barium is almost nil in most of the glasses, but in head type glasses it is there. Silicon almost steady. Potassium very less content. Calcium is, so this is okay. This has some outliers like this, and also iron is quite less. Iron most of the time it is near to 0, but in some of the cases iron is provided more. That fitting is more. So this was mainly the classification. Or now let us try to build an algorithm and try to predict on the basis of k nearest neighbor. So here I have number of observation 214. Now I will take 200 as my training, and I will try to train a test on 14. So 214. This will be my split. So as I said earlier, standardization is quite required when I am working with KNN. So I will scale to the same scale. That is, my mean will be 0 and standard deviation will be 1. And for that, I have a simple statement in R scale, where center equal to true and scale equal to true. So center will be that my mean will be 0, scale will be my standard deviation will be true. So by default, I think these are true, but I've still made them. So this is my standard. So if you remember, for the first time, it was only greater than 0. A quantity of an element cannot be less than 0 or cannot be negative. But after scaling, if you see, it varies from -2 or even more. So this is what scaling does. Puts them under the same scale. Similarly for other element as well. And if we try to view, I have taken aluminum and refractive index. And if I check first three values of X, I have aluminum and refractive index, and these are the. So now let us try with value of k equal to 1. I have set my k equal to 1, and with uh, first nearest neighbor I will try to predict that what will be my dataset classified as. or how that labeling will be done on the rest 14. So see, in the initial data set or the original one, these 14s were labeled as WinF, WinF, this was WinF. So in nearest neighbor 1, it is correctly classified. All of first 7 are correctly classified, but in nearest neighbor 7 or 5, sorry, this particular one is incorrectly classified, WinNF. So there is a misclassification here. Otherwise, here also it has been classified quite well. In both the cases, it is classified to head. So this could be a effect of noise, as head could have been the most nearest one, but it was due to a noise. Again, Win and F has been correctly labeled here. Now these two, 13 and 14, originally I have con and table, but in nearest neighbor 1, k equal to 1, these are classified as head, and in nearest neighbor 5, these are classified as Win and F and head. So these two again are misclassification and could be due to noise, induced noise that is there. So let us make a plot and try to see how this goes. So see, these are the plot that I have, and each of the figure, or I should say the color, has a meaning. So if you see, so black is for win F, red is for win NF, and so on. And these are how they are classified here. Now let's say these are for 200s. That was my that was there in the train. Now let us put the points of test as well, and let us see how they have been classified. So as you can see, the bold dots or the bold points here. So this is more it was more nearer to red, so it has been classified as red, and it is for one nearest neighbor. That is value of k is 1. So I think there was a red value here, so that's a black value here. For that reason, this has been classified as min f. Again, same for this. There was some black values here as well. Also, there was a congestion of red values here, so these two are classified as red. And also, this part was more pink, so these three were classified as pink. So more or less okay, but there were some misclassification. Mhm.
Ankit, can you zoom this picture?
Okay, okay, okay. Sorry, sir. I'm extremely sorry. Yeah. So this is how it is. So as you can see, this one was black, so it has been classified as black. And here also, as because it was one nearest neighbor, so here just beside this black one, you can see here it is a black also, just beside. So this has been classified as black. Here also, this there were black congestedly placed, so this is also a black. Similarly, here also this black dot, a range of a cluster of black, so this is also black. Here also most nearest one was red, so this is red. And here also the most nearest one was pink, so pink. So this is for n equal to 1. Oh, sorry, k equal to 1 for one nearest neighbor. Now if I have 5 nearest neighbor, now I am considering, and let us try to see how it goes. Now if I try to zoom and see, so here if you see, there is a bit change in the classification. More or less it has been, it is same, but as we have seen there, as the range increases, the number of neighbors that are considered to be that are considered for the classification changes. My classification also changes slightly. So there is a bit difference here. Otherwise, more or less the results are same. So we had difference for only few of them. I think there was a difference for 6 number. It should have been WinF, and here it was WinF in 1. But in 5 it was misclassified, and the difference should have been here in 13th one. Head and WinF, NF. So let us see how many were correctly classified and how many were misclassified. So here what I'm making is I'm making the sum of all the true values and dividing it by 14. So this value is 14. So try to calculate what is the percentage of correct classification. So for 1, I have 78% correctly classified. So out of 14, 78 correctly classified, 78% out of 14. And here, if I have considered it 5, so 71. So this is not a much big indicator, because if you see, uh, the numbers are 14, number of points here, and in that, if there has been one or a single change, single misclassification that is there, so that would have impacted this 7%. So this doesn't make much of a sense here, because the numbers that we are dealing with is quite less. So that is okay. So how to decide upon the value of k? Now here we come to a method that is cross-validation. So what I will do is I will run a for loop where I will vary the value of k from 1 to 10, and I will try to predict that for which value of k I have got the best classification, or the percentage that I have got is the best. So now if you see, for k equal to 1 I have 62%, 61, 61, so on, 64, then almost steady 62, 63, 63. So here for this value I am getting a better number. So this is 1, 2, 3, 4, 5, 4, 5. Yeah. For 5 I am getting a highest percentage. Similarly, if I try to plot it, so it was like this. So it was so the range of scale is not quite high. It varies from 61 to 65. So this is how it looks like. So for the value of 5, I have here the highest accuracy, and then it almost stabilizes or remains the same. So now it was only on the basis of two variables, that is refractive index and aluminum. Now let me try to do it with all the variables that were there. So for here in X, I was considering only refractive index. Now I will consider all the 9 and try to make the classification, how it works. So here, if I see the classification for one nearest neighbor, quite high misclassification, more prone to noise. If you can see, more prone to noise. And if higher value of k, it is more or less steady. That misclassification is quite less here. So rather, I can see only a one case of misclassification. Otherwise, more or less, it has classified correctly, right? So less value of k, more prone to noise, and as I increase the value of k to an optimum level, it stabilizes. Now let me see the percentage accuracy. Now, and for 5, I have 92. So only one was misclassified, otherwise all of them were correctly classified. So here if I see what are the values for which I am getting an optimum value, so 70, 70 and 71. So at value equal to 3, I am getting a better value. Otherwise it goes down again. So 3, for 3 value, I am getting the maximum. So this code is mainly for KNN.CV. CV means cross validation. So it cross validates on itself and try to make a prediction. So this is a good way to actually make a cross validation. So whenever we are working with a supervised data set, we can do this cross validation, and we don't have this leverage or this I would say, that liberty to work with this cross validation when we have unsupervised, when we have to make our own decision and try to understand that which one works better. One more data set that we will look at is German credit data. So this data set that we have worked yesterday or day before, if you remember, on logistic regression, we have used that German data set, German credit risk. So now we will use that data set again and try to do it with KNN and try to understand that how it works. So German credit risk, German credit, yeah, here I have. So this is my credit data on 1000 observation that I have. So again, as I said earlier, it was default. Does the person defaults or not? And these are the codes that I have to change it into my correct labels. So let us do that. So I have a R code written for that already. I will do that and let's check the results. So here I have transformed it, and what was only as a label or as a sign, now I have changed it into a correct format that I need to work with. So this is quite readable and quite well understood. So let us work with this and try to understand that how I can work with this. So let us work only with few variables for the time being. So here I am working with only the continuous variable, my duration, the amount that is there, and the installments that I have to pay. And I have scaled them. As I said, for KNN, scaling is quite required. All of them should be in the same scale, so one doesn't dominate over the other. So let us make a train data set and do this. For n equal to 1, let us make a classification and now. So here I have training data set. I have taken around 900 and 100 has been left out as my test. So I'm checking it only from 1 to 10 and let us having a sample on checking that how well it has been classified. So here I can see in original data set this was 1. Here for nearest neighbor 1 it is 1 and nearest neighbor 3 it is 0. So a misclassification. Here both of them are 1. So this would be a probable noise. More chances of this person was to have 1, but this person did not default. Anyway, this person defaulted, and on the basis of nearest neighbor, we predicted that he has defaulted 0 0. This is again a 1 1 for both of them. So quite less likely that he was a non-defaulter. But again, classification is steady. Again, a misclassification for both of them, and here again a misclassification. So nearest neighbor 1 here works better compared to nearest neighbor 3. So let us calculate the percentage and now try to understand. So here I have 100 in observation in the test data set. So that is why I'm dividing it by 100. So how many I got it correct, and I'm making a sum of it out of 100. So for nearest neighbor 1, 60% accuracy, nearest neighbor 3, 61% accuracy. So on overall level, both are more or less same. I cannot make a claim that this is better because this is very insignificant increase or improvement. So on basis of this, let us have a plot and try to understand on nearest neighbor 3 that how it has been. So this was actually label of installment percentage 1, 2, 3, and this is how it has been done on the coloring, and also this is for default data and my prediction. What was there in the data set and what I have predicted. So yeah, it becomes quite hazy, but as you can see, the classification here is on the basis of nearest neighbor. So could be possible that not considering all the variables was the reason of low accuracy, and there could be other factors as well. So more or less, this is how it works, a KNN algorithm. So here also let us try to make a cross validation and try to see what is the optimum value of K or the best value that we should choose. So here 61, 61, 64 for value of 3, 62, 64 again for 5, 65, 6, 65, no, 67, 66, 67. So this value we are getting better. So this is 8, value of 8. For this we are getting the highest value. So this was all about K nearest neighbor. Now there is a problem to this that it doesn't ends there. So this was the overall concept, but there is an extension to KNN algorithm. What is that? We will see and try to understand. Now, if you see here, consider just this example. This is my point, and this is more nearest to me. For k equal to 1, it is okay. It has classified it like this. Very good. For k equal to 3, my classification changes and it goes to class 2. So, does it seem appropriate? Should it does it not look like that it should have been a box instead of a triangle? A box seems more appropriate here. So how to mitigate this drawback? So there we have a concept of uh, distance weighted nearest neighbor. What happens is we divide the or we divide the summation of the Euclidean distance by particular, or the weight to the distance is given more. What happens is uh, here this sample is more closer, so this will be given more weightage as per the weight or as per the distance that it has. Again after that this will be given weightage, and again after that this will be given weightage. So I give weighting to each of the nearest neighbor on the basis of the distance with which the or how far is the sample placed from my location. So there we have a concept of uh, distance weighted KNN. So in KNN, the votes of nearest neighbor were taken, but in distance weighted KNN, what happened is my priority is given on the basis of the distance with which it is placed, how much far it is from my location. So the weight the contribution of each of the k neighbors with respect to their distance. So here I have divided this by my weight factor or my distance. So on the basis of this, what happens is more robust to noisy instances and outlier. So this is a good way to actually mitigate my outliers and noises. A very good way. So this weighted and distance weighted KNN you won't find at much places. Even I discovered this method after long research when I was doing on internet. So thought of explaining this because this is a very good way to actually mitigate noises and outliers. So same thing, nothing more. So let us take a case study and try to understand. So this is a iris dataset that we have. Iris dataset, you all must be familiar with this. Most used dataset for training or for illustration of clustering. So here I will be working with distance weighted KNN, and for that my command becomes kknn. So here it has probability settles. So here I have my original versus my fitted based on the uh, weighted distance KNN. This is how it has been classified. So 16 has been correctly classified. Here is one misclassification, and here 20 are correctly classified. So good classification here, I can say. So here the entire iris dataset consists of 150 data where I have taken one third as a test. So here you can see m by 3. So out of 150, 50 has been taken as test dataset. So if you all of these, this adds up to 50. So I was trying to test on 50, and here I can see only one misclassification is there. Otherwise, it has been quite well classified. Only one misclassification. So a very good performance. So So here the one with misclassification, you can see it is there in 2. Otherwise all the green are correctly classified. Only a misclassification here. So it works quite well. So this was a simple example of iris data set and how weighted distance KNN works. So that's all for today. And as an end note, that this is a very good algorithm to work with. And when I'm working with weighted distance KNN, then I'm expected to have even better accuracy because I take a mitigating effect for all my noises and outlier. And also this works quite well. Uh, the speed also, and also very easy to explain to others. So any questions that we can take or any doubts, let me know. Okay then, thanks for joining in. Thanks everyone, and we will meet you for the next and for the next session will be on knife based classifier, that will be tomorrow, and on text analytics. Thanks everyone, see you tomorrow.